হ্যালো, হ্যাঁ প্রবীণ, ফারুক জয়েন করেছে। ফারুক খোঁজ করছিল যে প্রবীণ জয়েন করেছে।
ঠিক আছে প্রবীণ, হ্যাঁ আচ্ছা।
দশ মিনিট মতো সাইলেন্ট করে স্টার্ট করে দেবো। 10 মিনিট আমি দিচ্ছি, ঠিক সময় পাঠিয়ে দিচ্ছিলাম একটু পর। আমি আমাদের স্টুডেন্টদেরকেও বলেছি স্যার জয়েন করতে।
হ্যাঁ হ্যাঁ,
ভালো হয়েছে,
অনেকে এই তো অনেকে করেছে।
আচ্ছা আচ্ছা আচ্ছা, আমার মনে হয় যে ইউ ক্যান গিভ অল দি স্টুডেন্টস দোজ হু আর ইন্টারেস্টেড।
হ্যাঁ আমি দিয়েছি। আমি দুটো সেমিস্টারের স্টুডেন্টদেরকে দিয়েছি অলরেডি।
ও ভেরি গুড, আচ্ছা ঠিক আছে, হ্যাঁ। বিকাশ দা গতদিনে কেমন হলো?
গতদিন ভালো হয়েছে।
আচ্ছা গুড।
প্রফেসর সম্মুখ রায়চৌধুরী ছিল।
হ্যাঁ আমি ওটা শুনেছি, ওটা শুনেছি আমি।
আর কনক, তুই হ্যাঁ ইউ আর দেয়ার, কনক ছিল এন্ড কন্ট্রিবিউটরি সবাই
আচ্ছা
ভালোই বলেছে।
বাহ, গুড গুড।
Everybody from Bengal.
Oh.
Everybody from Bengal.
আচ্ছা আচ্ছা।
So all relativity people joined.
না তার মানে এখন লার্জ নাম্বার অফ, মানে আমাদের এখান থেকে লার্জ নাম্বার অফ পিপলস এরা ইন্টারেস্টেড এখন মানে রিলেটিভিটি, কসমোলজি,
Relativity করছে। হ্যাঁ হ্যাঁ হ্যাঁ। Oh sorry, only তিনজন বাদে। তিনজন হচ্ছে from Lucknow University.
আচ্ছা আচ্ছা আচ্ছা, গুড।
হ্যাঁ। তবে আমাদের ওয়েস্ট বেঙ্গলের বিভিন্ন ইউনিভার্সিটি থেকে বিভিন্ন রিসার্চ স্কলাররা পেপার প্রেজেন্টেশন করেছে। এটা একটা খুব ভালো লক্ষণ।
বুঝতে পেরেছি, মানে অলমোস্ট সব জায়গায় কাজ করছে লোকজন আর কি এখনই।
সব জায়গায় লোকজন কাজ করছে, কলেজেও করছে কেউ।
ঠিক ঠিক ঠিক, এটা খুব গুড সাইন।
আচ্ছা স্যার, আমি একটা কোশ্চেন করতে পারি?
হ্যাঁ হ্যাঁ বলুন।
হ্যাঁ বললাম যে স্যার হচ্ছে ওই মানে আইসিএআরডি যে প্রোগ্রামটা, এটার জন্য স্যার এটা কি মানে এটা তো একটা পড়াশোনার মতোই?
আইসিএআরডি আইকার
হ্যাঁ
হচ্ছে রিসোর্স সেন্টার, আগে এটা নাম ছিল। ইন্ডিয়াতে টোটাল 5টা আইআরসি ছিল, তার মধ্যে নর্থ বেঙ্গল ইউনিভার্সিটি একটা, রাইট? এবং আরো হচ্ছে তোমার যাদবপুর ইউনিভার্সিটি। এখানে যাদবপুর ইউনিভার্সিটির অধ্যাপক আছেন প্রফেসর ফারুক রহমান। তারপরে ছিল কোচিন ইউনিভার্সিটি, দিল্লি ইউনিভার্সিটি, রায়পুর ইউনিভার্সিটি, এই 5 জায়গায়। তো এর উদ্দেশ্য হচ্ছে ন্যাশনাল সেমিনার, ইন্টারন্যাশনাল সেমিনার, ভিজিটিং প্রোগ্রাম। কেউ যদি কোনো রিসার্চ করতে চায়, কোলাবোরেটিভ ওয়ার্ক করতে চায়, বা টিচারের সঙ্গে কাজ করতে চায়, বা কোনো পরামর্শ নিতে চায়, দে ক্যান কাম টু দি আইআরসি
আচ্ছা
এবং এখানে
হ্যাঁ।
সেই কাজ করার সুযোগ সুবিধাটা আছে। আই কার্ডও
মানে
তাই। আই কার্ডটা
হুম
হচ্ছে অ্যাস্ট্রোনমি অ্যাস্ট্রোফিজিক্স যারা রিসার্চ করে তাদেরকে একটা
হুম
ভিজিটিং প্রোগ্রাম এখানে আছে। ভিজিটিং প্রোগ্রামে কি করা হয়, একটা ছোট্ট ডিএ দেওয়া হয়, আর ওই সেকেন্ড ক্লাস যারা যদি স্টুডেন্ট হয় সেকেন্ড ক্লাস 10 ফেয়ার,
হুম
আর যদি টিচার হয় তাহলে 3 AC 10 ফেয়ার দেওয়া হয়। তারা
হুম
এখানে
হুম
এসে কাজ করতে পারে উইথ
আচ্ছা
প্রায়র পারমিশন
আচ্ছা
ফ্রম
মানে স্যার আমরা
আই।
আমরা যখন এখন এমন যখন ফার্স্ট ইয়ারে পড়ছি মানে ফার্স্ট ইয়ার কলেজে পড়ছি তারা কি মানে এটা মানে যোগ দিতে পারে বা এরকম কিছু করতে পারে?
ফার্স্ট ইয়ার কলেজে হবে না, এটা
হুম
হচ্ছে মাস্টার ডিগ্রি ফাইনাল ইয়ার হতে হবে
আচ্ছা
অথবা
হ্যাঁ হ্যাঁ
রিসার্চ
হ্যাঁ
করতে হবে। অ্যাটলিস্ট
আচ্ছা
রিসার্চ স্কলার যারা জাস্ট জয়েন করেছে তারা
হুম
এটা সুযোগটা নিতে পারে।
আর এটা স্যার কোন কোন ফিল্ড থেকে হতে পারে?
অ্যাস্ট্রোনমি অ্যাস্ট্রোফিজিক্সে যারা কাজ করে তারাই।
হুম মানে স্যার ফিজিক্স ব্যাকগ্রাউন্ড কি লাগবে না অন্যান্য ব্যাকগ্রাউন্ড থেকেও হতে পারে?
ফিজিক্স ব্যাকগ্রাউন্ড ছাড়া তো তুমি অ্যাস্ট্রোনমি অ্যাস্ট্রোফিজিক্স কি করে পড়বে?
না, তবে
হুম
আমাদের
অ্যাপ্লাইড
হয়নি।
ম্যাথমেটিক্স থেকেও পড়ায়,
অ্যাপ্লাইড
হ্যাঁ হ্যাঁ
ম্যাথমেটিক্স থেকেও করা যায়।
অ্যাপ্লাইড ম্যাথমেটিক্স গুলো চলবে।
আচ্ছা আচ্ছা
অ্যাপ্লাইড ম্যাথমেটিক্স থেকেও করা যায়। বিদেশে তো যারা ইঞ্জিনিয়ার তারাও করে, কিন্তু আমাদের ভারতবর্ষে এখন এটা শুরু হয়নি।
না কারণ স্যার আমি
সুতরাং
ইঞ্জিনিয়ারিং করছি, তো আমি ইঞ্জিনিয়ারিং করছি বাট বিষয়টা ইন্টারেস্ট আছে এই জন্য আর কি বলছি।
ও আচ্ছা আচ্ছা।
এই জন্যই স্যার জিজ্ঞাসা করে নিলাম যে ব্যাপারটা আর কি আসলে।
হ্যাঁ। না, বিদেশি ইঞ্জিনিয়ারদেরকেও দেওয়া হয়, কারণ ইঞ্জিনিয়ারিং এও
হুম
ওরা অ্যাস্ট্রোফিজিক্স একটা টপিক নিয়ে পড়াশোনা করে। টেলিস্কোপ
আচ্ছা
মেকিং ইয়েতে
হুম
এগুলো আছে।
আচ্ছা আচ্ছা
Okay, we
থ্যাংক
are
ইউ
very
স্যার।
near to the time. So, good morning and welcome to you all in the seminar, National Seminar on Recent Advances in Astrophysics and Cosmology. Today, in the morning session, we have speakers from Jadavpur University, Professor Dr. Farooq Rahman and Dr. Rajibul Islam from IIT Kanpur. So both the talks will be in the morning. Before giving it to the chairman, I introduce Professor Farooq Rahman to all of you. Professor Rahman is elected a fellow of Royal Astronomical Society, London, UK. He did BSc from St. Xavier's College, MSc in Applied Mathematics from Calcutta University in '94, and PhD from Jadavpur University in 2001 under Professor Shubinoy Chakraborty, I think. Farooq? Yes.
Exactly.
Exactly. And he had 20 years of teaching experience and 24 years of research experience. He has written 3 books with Professor S.S. Dey and 2 others independently on special theory and general theory of relativity. He, under his guidance, 28 PhD came out. It is a huge number. 28 research scholars came out. Now he is guiding around 8 research scholars. His field of research is relativity, cosmology, topological defects, black holes and wormhole physics, gravastars, cosmic coincidence problems, galactic dark matter, and theoretical astrophysics, compact objects, and the recent hot topic in cosmology, that is the modified theory of gravity, and on accretion disk around a black hole. He has a huge number of foreign collaboration around 30 with Canada, South Africa, Russia, USA, UK, Brazil, Spain, Kazakhstan, Iran, Italy, Egypt, and many more countries. Also, he has national collaboration with Aligarh Muslim University in India, North Bengal University with Professor K.K. Nandi, then Aliyah University with Mehdi Kalam, Vishwa Bharati, St. Joseph College, Shibpur, and many more universities in India. His publication is around 330, which is a huge number, 330 publications. So today we have a notable speaker, and I am handing over this to Professor Chairman Sir, Professor Prabir Kumar Haldar. He is Dean of PG Faculty of Science at Kuchbihar Panchanan Burma University, Kuchbihar. Professor Haldar is also working nowadays in varieties of field, in cosmology, in material science, in fiber optics, and other fields of physics. So he has a versatile experience in different area, and I request him kindly take over it as a chairman of the session.
Thank you, sir. It is a matter of great pleasure for me among the galaxy of students, MSc students, research scholar, PhD student, postdoc students, and respected faculties members. I am thankful to the organizer for giving me an opportunity to act as a chairperson in these sessions. I would like to thank Professor Vikas Chandra Pal to organize the national seminar on recent advances in astrophysics and astronomy in cosmology. Now today our speaker is Professor Farooq Rahman, Professor of Jadavpur University in mathematics department. I know him very well. He's an outstanding researcher. Just I given some example. He has a Google Scholar citation about 5,700, and in this 2020 he has a citation about 1,000 citations. So that is remarkably proves that how he has done something extraordinary in field of the astrophysics and cosmology. Our Professor Vikas Chandra Pal already in the institutes, and he has many collaborators in our country and across the world. So I would like to welcome Professor Farooq Rahman to deliver his lecture.
Okay, thank you, Prabir, for introducing me. And at first, I am thankful to Vikas Da for giving me a chance to say something on this national seminar. So I am mainly interested to choose this topic, particularly for the research scholar and young researcher. So I will start now. Share it. It is visible. Hello, can you hear me?
Yes,
Yes.
it is visible.
Okay. Now my topic is shadow of wormholes. Actually, in the weak field design, general relativity is extensively tested and confirmed, but this is not the case for strong field design. there are theoretical and observational concerns about the viability of the theory for strong gravitational field. I mean, around black holes, wormholes, or neutron stars. Now, determining the parameters of a compact object is made mainly by optical observations, which are quite inaccurate because of the size of these objects. Therefore, a good tool for this purpose could be the usage of shadows, that is a dark region over a luminous contextual. Now, one can recognize the shadow of a black holes or wormholes as a result of strong gravitational lensing, generating a dark spot in the sky of a remote reviewer. The shadow is actually an optical look exhibited by the black hole or wormholes when there is a source of light from stars, accretion flows, etc. around it. This manifestation has been investigated theoretically as well as observationally by the application of very large baseline interferometry, that is VLBI techniques at sub-millimeter wavelengths for studying the shadow cast by supermassive objects, including the ongoing ambitious project involving the compact astronomical radio sources Sagittarius A in our galaxy center. Now, being at sub-millimeter wavelength, this technique significantly reduces the interstellar scattering and may allow to see beyond the compact synchrotron emitting region around Sagittarius A, since this region is expected to become optically thin at sub-millimeter wavelengths. Also, VLBI experiments can reach a resolution of the order of angular size of the gravitational radius of Sagittarius A. Thus, the space-time geometry could be determined through the analysis of shadow in the vicinity of photon sphere. And look at this artistic picture of black hole shadow cast by static accretion. Now, compact objects can cause extreme local deflections of light and can bend light by an arbitrarily large angles, causing the formation of light rings, which are circular photon spheres, possessing distinct phenomenological signatures in terms of both electromagnetic and gravitational waves. And since this shadow outline depends on the gravitational lensing of nearby radiation, its proper surveillance can provide evidence about the parameters as well as space-time geometry around the black hole or wormhole. Now, light propagation, that is the null geodesic, in the compact objects, space-time, maybe black hole or wormhole space-time, can be perceived in two ways. Trajectories which escape to distance observer, and number two, such that they are captured by the compact object. Therefore, a black region appears in the viewer's sky, creating a shadow. The boundary of the shadow can be resolved by the black hole or wormhole space-time metric itself, as it relates to the appearing shape of the photon detent objects at observed by a remote viewer. Hence, important astrophysical information can be obtained from the observation of the motion of a gas stream in the gravitational field of the compact objects. Now, since I am interested in wormhole in lucid sense, wormhole are hypothetical handles or tunnels in space-time linking widely separated region of our universe or entirely different universe. This is an artistic picture of a wormhole. One can go from one space to other space or one region to other region by using the wormhole. There is shortcut path. It takes very short time. So I do not give the details because in the next lecture, Dr. Razibul, the renowned scientist, will say something about wormhole. So I just mentioned what is wormhole in the lucid sense. Recently, we have shown that the galactic halo possesses some characteristics needed to support a wormhole. This is the first example, I think, the possible existence of wormhole in the galactic region. And after the publication, Science News wrote a review on this paper. Now later, we have shown theoretically that dark matter yields a wormhole-like spacetime in the central part of the halo. And this result is an important complement to the earlier results, and thereby confirming the possible existence of wormholes in the most of the galaxies. And this report has been published in Annals of Physics. And after the publication, this discovery has been converting most of the leading newspapers around the globe. Now, since wormholes are specific type of astrophysical objects, so it has been an active area of research to study the shadow of wormholes as well as the shapes of the shadows. The shadow of compact objects is an outstanding investigation by studying the signatures of the wormholes versus black hole. Having all the above in mind, here we analyze the shadow of asymptotical flat and axially symmetric wormholes given by the parameterized metric, which possesses sufficient symmetry for the separation of variables. So we consider a general stationary axisymmetric space-time metric described a TO class, rotating traversable wormhole in Boyle-Linkist coordinate TR theta phi, which is given by this metric. Just 1 minute, I just take this one. Okay, good. Now we see that the metric function in B K omega depends on only r and theta coordinates. Now, this metric actually generalized rotating form of the static Morris-Thorne wormhole metric. Therefore, the metric function must have some restrictions which led to the specific geometry and significant properties of the wormhole. The function in which regulates the gravitational redshift is often called a redshift function. In order for the wormhole to be traversable, one has to endorse that there are no curvature singularities or event horizon. Therefore, the redshift function n should be non-zero and finite all over the region, that is from the throat to the spatially infinity. The function b, which is known as shape function, this function b is known as shape function, which regulates the shape of the wormhole. It is always non-negative and possesses an apparent singularity at r equal to r0 equal to b that associates with the throat of the wormhole. The function b should be independent of theta to avoid any curvature singularity at the throat. That is, it obeys the restriction del b del theta equal to 0. Another important constant is the flare out condition at the throat, where del b del r at the throat r equal to r0 should less than unity. The function k, this function k is a regular positive non-decreasing function defining the proper radial distance r equal to capital R equal to small r k measured at theta point from the origin. Now, for our purpose, we use the specific form of redshift function and shape function, which is given by this expression. This form of shape function and redshift function proposed by Konoplia in 2016 in the paper in JCAP. Just 1 minute. Take this one. Okay. Now here A is the spin parameter. A is the spin parameter. This A is the spin parameter. And this wormhole has mass m and throat R0 greater than twice m. You always remember this results. Now, an ergo region may present around the throat of a rotating wormhole. This region can be determined when the metric coefficient GTT is greater than equal to 0. And for ergo sphere, this GT equal to 0, which gives this equation. And also, the critical angle can be determined at the throat of the wormhole by this expression. Further, the ergosphere will only exist when the spin parameter A crosses the critical limit, where sin theta equal to 1. One can remember this. And for our wormhole metric, we just take m equal to 1, throat radius 2.2, which gives critical value is 0.729657. And the ergo square of our wormhole for these values can be seen in this figure, where the blue circle is the wormhole throat and red dashed surface are the ergo surface, and one can get the ergo region in between these two curves, that is in this portion. It's in this portion. This is the ergo region for our wormhole metric for the specific choice of m and throat radius. Now, when a wormhole is in between a star, that is a bright source of light, and a viewer, the light comes to the viewer after being deviated by the gravitational field of wormhole. However, certain portion of the photons, actually with small impact parameters, originated by the star and end up falling into the wormhole, that is not able to reach the observer, giving as a result a dark sector in the sky, which is called shadow. The boundary of the shadow apparently is determined by the unstable circular photon orbits. Now, in order to find the unstable orbit, one requires to the study of geodesic configuration. Therefore, to study the geodesic configuration, one needs to Lagrangian. So, from our wormhole metric, one can write the Lagrangian, and this Lagrangian comes from this metric. This Lagrangian comes from this metric. From this metric, one can easily write the Lagrangian, and the Lagrangian, one can see that this Lagrangian does not depend on p and theta, p and phi. And as a result, we have two constants of motion, which are energy and angular momentum in the direction of the axis of symmetry of the photon. And using this formula, that is this well-known formula, one can get the expression for E, one can expression for actually not PT and P phi, which is equal to L, and PT is equal to E, their energy. And this two equation gives the four velocity component. One can easily find from these equations. Now, the Hamilton-Jacobi method determines the geodesic via this equation, where S is the Jacobi action and lambda is the affine parameter along the geodesic. And to solve this equation, this is a very complicated equation, but one can solve it by using the separation of variables, method of separation of variables. And we take the solution of this Jacobi action as a separable form, which is given by this separable form as a solution of Jacobi action. Here mu is the mass of the test particle, and for photon definitely mu is 0. For photon mu definitely is 0. that is we choose as test particle, whether maybe massive particle or photon. So for our purpose, we choose photon, so mu should be 0 for our purpose. Now, inserting these separable forms in the Hamilton-Jacobi equation, one can get the solution for S theta. Also, one can get the solution for SR, which is given by this expression, these two expression. But Q is known as Carter constant. And also, also using the formula that is PR equal to del S is standard formula in classical mechanics. One can easily find the other 4 velocity, that is r dot and theta dot, where we r and t, capital R and T is given by this expression. This two expression is very crucial for our purpose, so we should remember the form of R. Now, after finding SR and S theta, we ultimately get the form of the Jacobi action S, which is given by these expressions. You see that the geodesic equation in stationary and axial symmetric spacetime are parameterized by the constant of motion. Actually, there are 3 constants of motion, that is E, L, and Q. However, geodesic motion of a photon described by 2 independent parameters. For our purpose, we use as 2 independent parameters. We just redefine the parameters is like this. One is xi and one is eta. This duly defined parameter is known as impact parameters. This is very, very crucial for our purpose. So we should remember the term impact parameters. Now, 2 regions of spacetimes are joined through wormhole, that is a tunnel-like structure without any horizon or singularity within it. Now, let's assume that the photons are coming from a star towards the wormhole. Actually, it is placed between the observer and the star, and illuminate one region, and no light source are remaining in the neighborhood of the throat in the other region. In the first region, the possible orbit of the photons around the wormholes are: number 1, orbits entering the wormholes and passing through its throat, and number 2, dispersed from the wormhole to infinity. Now, a remote reviewer will capable to observe only dispersed photon. You should remember, a remote reviewer will capable to observe only dispersed photon from the wormhole. However, the photon captured by the wormhole will form a dark patch, and this dark region detected on the bright background is known as shadow of the wormhole. You should remember this. Now, how to find the wormhole shadow? Now, to find the wormhole shadow, there is a dark region in the viewer's atmosphere in the presence of shiny background. One will start to find the critical orbits that separate the escaping and falling photons. Actually, our prime motive is to estimate these critical geodesic or unstable circular orbits. You should remember this. We have to interested to find actually the critical geodesic or the unstable circular orbits. In order to acquire the boundary of the wormhole shadow, one needs to study the radial motion of the photon around the wormholes. The critical orbits, I mean, they are described by the impact parameter xi and eta. I just mentioned, I have mentioned. The critical orbits distinguish the dispersed and captured photon. A slight disturbance in this critical values can change it either to escape or to a captured orbit. As a result, the critical impact parameters describe the boundary of a shadow. Thus, the boundary of the shadow is determined by the unstable circular photon orbits. This is very crucial. So, to find the boundary of the shadow is Actually, the shadow is determined by the unstable circular photon orbits. Now, by studying the radial geodesic, one can calculate the circular orbit, which can be expressed in the following energy conservation equation. This is one-line calculation one can easily find from the geodesic equation to reach this equation, where VEF actually is the effective potential that describes the geodesic motion of the photon around the wormhole. Now, the null geodesics are divided into two classes depending on their impact parameters. Number one, trajectory of the photon passing through the wormhole. Number two, orbits of the photon dispersing to infinity. This is very crucial. So, number one, the trajectory photons passing through the wormhole and orbits of the photon dispersing to the infinity. We should remember these two results. The boundary among the two classes is designed through a family of unstable spherical orbits, which follows the criteria, these three criteria or these three conditions to design the family of unstable spherical orbits. Now, actually, the first condition comes from the fact that the radial motion has a turning point r dot equal to 0 when the photon will scatter from the wormhole. And the last two conditions, this is last two conditions. So last two conditions are due to the maximum of the effective potential for the critical orbit between escape and falling motion. Now, we rewrite the above condition in terms of R. We have already defined the expression for R. So we just read out the above the three conditions in terms of R. This one-line calculation one can easily check it. Now, using the equation R and dr d equal to 0, one can find two expressions for the impact parameters eta, xi and eta in terms of radial coordinate and of the unstable circular orbits, which is given by these equations. And for unstable orbit, 1 minus Vr vanish, and one can get V effective equal to 1. And therefore, the unstable circular orbits located at the throat, the second condition can be reduced to this expression. Oh, for calculation, we need this equation, where the subscript 0 implies the function are defined or evaluated at the throat. So that means k at the throat, n at the throat, or omega at the throat. Now, for the set of unstable photon orbits, above sets of equation express the critical locus of the impact parameters. In other words, these equations space the boundary of the shadow in the impact parameter space. However, for true observation, the remote reviewer will see the apparent shape of the shadow in his sky. I mean, a viewer sky means it is a plane passing through the center of the wormhole and normal to the line linking it with the viewer. Now, the celestial coordinates connected to the actual astronomical measures that span a two-dimensional plane, which is defined by these two equations. The celestial coordinate is alpha and beta are given by these two equations. Where this is RO, is the position coordinate of the remote viewer taken very large, that is far away from the wormhole. And theta O is the angular coordinate. Actually, it is actually the angle of inclination between the axis of symmetry of the wormhole and the direction to the viewer. Now, the celestial coordinates alpha, beta are the apparent perpendicular distances of the shadow image as observed from the rotation axis and from its projection on the equatorial plane respectively. Using the geodesic equation and values of the 4 velocity components, and after some simple algebraic manipulation, the celestial coordinate assume the following forms. Assume these following forms. And after knowing the expression of celestial coordinate and impact parameters, one can construct the shadow of wormhole. Now, actually, in alpha beta plane, this equation define the part of the shadow boundary formed by the unstable circular orbits which lie outside the throat. Now, this figure shows that the shadow of the wormhole for different values of the spin and throat size. Note that for a given wormhole size R0, say R0 equal to 2.5, the shadow shape deviates from the circularity as we increase spin. Now, one can see that for the spin, you take the spin 0.001, this is the shadow, blue line. Now, if you increase the spin parameter A as 0.2, the red line curve is the shadow. Now, thus, if we choose spin parameter as 1, then one will see that this is the shadow. Thus, shadow deviates from the circularity as we increase spin A. Now, this figure also, if you compare, actually, they compare the previous figure. That is for a given spin. That is, we take the spin as say 0.8, and if you increase the throat size of the wormhole, one will see that the shadow becomes more or more circular as you increase the throat size. One can see that R0, this is a blue curve, throat is 2.5. R0, that is the throat size is 3, then one can see the red curve. In this way, for R0 equal to 5, one can see the shadow which is more or less circular. So if you increase the throat size, then the shadow becomes more or more circular. Sorry. Also, we compare our result with those of Kerr black hole. Note that for small spin, that is A0 equal to 0, A equal to 0.2, or A equal to 0.05, or small throat radius, that is R0 is small throat radius. One can see that for small spin and small wormhole throat, its shadow mimics those from black holes. Now, actually here the shadow of wormhole is in red line, and shadow of the Kerr black hole is blue dashes line. However, if you increase either the spin or throat radius, increase throat radius or spin, the shadow of the wormhole start deviating from that of Kerr black hole. Now, detection of such deviation may possibly indicate the presence of a wormhole. This is very, very crucial. So, the figure indicates that for sufficiently large spin or throat radius, one can easily distinguish wormhole from a black hole configuration. Also, one can constrain the size and spin of the wormhole by using the result of M80 observation. For this purpose, one can use the average angular size of the shadow and its deformation from circularity. The region between two black dashes, this region, this and this region, two black dashes. So these two black dashes. Vertical lines indicate that the spin range 0.5 to 0.94. The horizontal, this horizontal red dashes line indicates that the critical throat size R0 equal to 4.76, below which both the size and deviation from the circularity of the shadow is consistent with the M87 results. Here we take the inclination of angle theta equal to 17 degree for drawing the plots. Thus, a wormhole having reasonable spin or throat size can be distinguished from a black hole through observations of their shadows. Thank you, and hope young researchers would show interest on this new approach to do advanced research on observational signatures of wormholes by studying the shadows in details. Thank you.
I would like to ask the students if you have any questions. Students, researchers, or faculties.
Yes, sir. I have a question.
Sure.
Okay.
Can I ask my question? This is
Sure.
Yeah, Himanshu Kumar from Dayal Singh College, sir. I'm faculty. Sir, I have a question. Like, sir, in the spin studies of the wormhole, can we just elaborate by adding the sort of different sorts of precession conditions, and then further carry out the study, talking about specific types of precession in the wormhole?
Yes, definitely. It's actually this is an open. My talk is related to an for future study. One can easily use the defined type of wormholes to find the observational signatures from the black holes. So you should use different type of wormholes and compare with Kerr black hole or any other rotating black holes. And if you find the significant difference of the shadow, one can easily detect whether that your unknown object will be the wormholes.
So excuse me, sir, I was talking about precession. Like spin we take as a parameter.
Yes.
Talking about specific type, like a precession, particular types of precession movements. If we just like a gyroscopic thing, we can imagine. Can you elaborate the spin there with some sort of?
So possibly you may, but at the time I don't able to answer your question. But I will think it. Thank you, Himanshi.
Okay, sir. I will ask you later on, sir.
Okay, no problem.
Thank you, sir.
Any questions?
Sir,
Sure.
বললাম স্যার ওই স্ক্রিন মানে ওটা কি স্ক্রিন
Sorry, I can't hear. Hello?
আচ্ছা শোনা যাচ্ছে স্যার?
হ্যাঁ শোনা যাচ্ছে। No, it.
হ্যাঁ বললাম স্যার স্পিনটার উপরে কি করে নির্ভর করে একটু বলবেন স্যার, ওটা একটু ক্লিয়ার করে বলুন।
কি করে নির্ভর না? You see that? If you draw, if you use the, can you see it? Can you see it? Hello?
Yes sir, yes
Okay.
sir.
Okay. Actually, if you want to see the shadow, then we have to use see it in your sky we call it as observer sky. And for this, we have to use the coordinates alpha and beta, which is called celestial coordinate. Okay, and these celestial coordinates depends on the parameters of the metric, I mean wormhole metric or black hole metric. And if the black hole or wormhole has spin, then these parameters should depends on the spin. So if you vary the spin, one will get the different type of shadow. It's clear? It's clear?
Yes, sir.
Okay, okay, good. Next, any other question? Or... Sure. Sure. Hmm. 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 Huh. Hmm. Exactly. Actually, this is actually the separation. In terms of mathematics, it is a separation constant to solve the equations. Okay. Yes, definite some physical relevant, but we avoid this extra term. We redefine the parameters, which is eta and xi. Okay, which is we can say it is a normalized. We just normalize it. Sure. Huh. Huh. Okay. Hmm. No, not extra parameter, but these two parameter depends on the three parameters. Okay. Because we want to draw the image in the observer viewer sky, and to find the coordinate system in all two coordinate system, that is in the plane, we just use the two coordinate system. One is alpha and beta. For this purpose, we use two parameters to draw the pictures. Okay, from the equation, we just after some mathematical manipulation, we transfer it into two coordinate system to draw the picture.
Okay, thank you. Thank you. I would like to mention another things. Professor Rahman has been also included to the world top 2% scientist in the research field on nuclear and particle physics, prepared by Stanford University, USA.
Oh, thank
So
you.
it is obvious our honorable organizer, Professor Vikas Chandra Pal, he is also the acclaimed scientist, and he is the member of the Royal Astronomy and Sciences. So I wish every success, Professor Rahman. So thank you.
Oh, thank you.
Thank you, sir. Thank you.
Okay,
So,
thank you because.
So our next resource person, Dr. Rajibul Sheikh, Department of Physics, Indian Institute of Technology, Kanpur, and he did his BSc from Krishnanath College, and MSc from Indian Institute of Technology, Kharagpur, and he did two postdoctoral, one from Indian Institute of Technology, Kanpur, and another renowned institute, that is the Tata Institute of Fundamental Research, Mumbai. And he has many collaborators in our country and across the globe. So I would like to request Rajibul Sheikh, please deliver your lecture.
So thank you, Professor Haldar, for the kind introduction. So I'd also like to thank Professor Paul for this invitation. So let me share my screen. Is my screen visible?
Yes.
It's visible.
Okay, so I'll talk about shadows of a certain class of curved black hole alternatives and constant them using M87 result. By alternatives, I mean horizonless or compact object which doesn't have any event horizon like black holes, or black holes or compact object which are black holes but whose space-time geometry deviates from the curved black hole. Usually compact objects can be broadly classified as following. So objects which have event horizons, those are called black holes. So in this black hole category, we can have curved black hole as well as non-curved black hole. And compact object which doesn't have horizon are called horizonless compact object. In this category, we can have a naked singularities, wormholes, or regular objects such as gravastar, etc. Of late, studies with regard to black holes alternative, which includes non-curved black holes as well as horizonless compact object, are becoming increasingly popular for a number of reasons. One of the most significant reasons is that these alternatives can offer us testing ground to probe the nature of strong gravity, that is to test any possible deviation from general relativity and to test the curved black hole hypothesis, according to which the space-time geometry around astrophysical black holes is well described by the Kerr solution of general relativity. Another significant reason is that some horizonless compact object may observationally mimic black holes, so that what we believe to be the signature of an event horizon may not necessarily be true.
Rajibul,
Yes.
sorry for interruption. Your slides are not visible. So slightly move up, I think. They are not.
Can you see?
Now visible.
Yes,
Now
now
visible.
it is visible.
Okay. So another significant reason is that some horizonless compact object may observationally mimic black holes, so that what we believe to be the signature of an event horizon may not necessarily be true. Moreover, the advent of the Event Horizon Telescope and the recent imaging of the center of the galaxy M87 have opened up a new era of observational astronomy to probe strong gravity. Therefore, it becomes essential to understand the characteristic signature of curved black hole alternatives. Yes. Yes.
I think Professor Rahman Farooq, you go out of you come out of the slideshow mode, right? That's why he can't show. Professor Rahman, yes.
Now is it fine?
Now you move it up.
Sorry.
Yes, it is visible now.
Yeah. Okay.
Your motivation is same.
Okay. Thank you. So therefore, it becomes essential to understand the characteristic signature of curved black hole alternatives. So in light of this, we study. I'll talk about strong gravitational lensing images and shadows. Let us now understand what the concept of shadows. So
hello, still I am on the screen. Hello.
It is okay, Farooq.
Huh?
It is okay. You stay in the. It is now okay. But Rajibul,
yes,
your now it is visible. Yes.
Okay. Thank you. So let us now understand the concept of shadows. So we observe shadows in our everyday life. For example, in this schematic diagram, so if we place a spherical ball in between a light source, which is denoted by this, and a screen. Then what we see is on the screen. Sorry, hello, is it fine? Hello.
Yes, visible. You go on.
Okay. Okay. So if we place a sphere in between this light source and the screen, then on the screen what we see is a dark disk. So this dark disk is the shadow of that sphere. And here notice that this shadow is a darker region over a bright background, which is this my screen in this case. Similarly, in everyday life, we see that buildings, trees, many other objects cast shadow on the ground when they abstract light from sun. However, in the astrophysical scenario, the concept of shadow is more or less similar with certain differences. So this is the shadow of the supermassive compact object M87. Here this darker region over this brighter background is what we call shadow. So in everyday life, the shadow is cast when object block lights from sun. However, in astrophysical scenario, the shadow is formed due to strong bending or strong gravitational lensing of light. Let us now understand the detailed theory, one which the detailed theory behind shadow formation by a compact object. So for this, consider this schematic diagram. So here we have a light source, we have an observer, and we have a central compact object which can be black hole or other compact object which may not have any horizon. Light from this light source undergoes gravitational, enters the gravitational field of this compact object, undergo deflection, and some of the photons may get captured by this central object and some may escape to a faraway observer. Now, we first consider the spherically symmetric case. Suppose we model the space-time geometry. Suppose we model the space-time geometry of this central object by this space-time. Now, photons from this light source, if they undergo lensing and reach a faraway observer here, then at the observer location, if we draw a tangent, then we will see that these tangents hit this green plane at some point alpha beta. And this plane is what we call observer sky. And this plane is this plane passes through the center of the space-time geometry and is perpendicular to the line of sight joining the observer and the center of the space-time geometry. And all the observation in this observer sky or in this plane is done using coordinates alpha beta, which we call celestial coordinates. Now in this gravitational field, if we usually the geodesic equation for photon are of second order. So if we integrate the geodesic equation and obtain first order geodesic equation, then these equations are given by this. Where in this radial geodesic equation, we have defined something called V, which we call effective potential. This effective potential is going to be crucial in the study of shadow. Here this xi and eta as well as b are known as impact parameters. These impact parameters remains conserved along a given light path trajectory. That means it doesn't change throughout the trajectory. Now, the coordinates alpha beta in the observer sky are related to the tangent of the geodesic of the trajectory at the observer location through this equation. Now, if we make use of the geodesic equation and put phi dot r dot theta dot r dot here and take the limit r naught tends to infinity, then we get these two expressions. Now here r naught is the radial position of the observer. Since the observer is far away, then we take that's why we take r naught tends to infinity. And theta naught is the observer's inclination angle. That is the angle between the line joining the observer and the space of the center of the space-time geometry and the z-axis. So in rotating case, z-axis usually coincide with the spin axis of the object. Hello, am I audible?
Yes, sir.
Yes. Oh, thank you. So let us now consider an example. So first we consider Schwarzschild black hole. So this is for understand. This is to understand in details how a shadow is formed. So if we plot the effective potential for this Schwarzschild black hole, then what we see is the potential have this form. Excuse me. So note that the potential has a maxima at r equal to 2m, and this r equal to 3m, sorry, and this r equal to 2m is the location of the event horizon. So we know in classical mechanics that the location of the minima of a potential corresponds to a stable circular orbit. But in this case, we have unstable, maxima of the effective potential. Therefore, the r equal to 3m corresponds to unstable circular orbit of photon. These unstable circular orbits are usually referred as light rings. Now, in spherical symmetric case, for example, so we have this space-time geometry set. This is the center. So if we take equatorial plane, then unstable photon orbit radius has radius 3m. If we take a plane which is not equatorial, say off equatorial plane, then the unstable circular orbits also has the same radius 3m. This is because of spherical symmetry. If we take another plane, then in that plane also we have the unstable circular orbit has radius 3m. This is because of spherical symmetry. So if we add all these unstable circular orbits or light rings, then what we get is a sphere of radius 3m, which we call photon sphere. Now, corresponds to this photon sphere, we define a critical impact parameter BC, which for the Schwarzschild black hole case is given by this expression. And this is equal to 3√3m. Now consider this schematic diagram that is shown below. So suppose, so this is the Schwarzschild black hole. So this is event horizon, say r equal to 2m. And this is the central singularity hidden within the event horizon. And say this is the photon sphere, the r equal to 3m surface. Now, if we shoot a photon from this light source with impact parameter, say greater than the critical impact parameter, then what happens is these photons get turned away by this effective potential barrier, and then it escapes to a far away, on the other side, to a far away observer, and this is denoted by this light ray. Now, if we denote the impact parameter by reduce the impact parameter little bit, but still it is greater than the critical impact parameter, then what happens is, before it escaping, it winds around the photon sphere, means it undergoes deflection more than 2 pi. And if the impact parameter is less than the critical value BC, which is denoted by this light ray in this effective potential plot, then what happens is the photon doesn't encounter the potential barrier. So what it does is it enters the photon sphere, which is denoted by this black circle. So the photon enters the photon sphere and then eventually get trapped and eventually get absorbed by the event horizon. So this photon is lost. How this photon is lost. However, if the impact parameter is just equal to the critical value, then which is denoted by this ray in this effective potential plot, and by this black trajectory in this plot. So if the impact parameter is equal to the critical value, then what happens is the photons critically or tangentially arrives at the photon sphere and settles down there. But since this photon sphere denotes the location of unstable photon orbits, that's why if we perturb that photon little bit in terms of impact parameter, then either that photons falls in or it escape to a faraway observer. Therefore, if we put a light source here and then observe from other side, then what we see is photons having impact parameter less than the critical value. Those are absorbed by, since those are absorbed by the black hole, so those photons create dark spot in the observer sky. And those photons which have impact parameter greater than the critical value, those photons create, since the observer receives those photons create bright spot in the observer sky. Therefore, if we collect all the dark spot and take a union of them, then what we see is a dark disk having radius equal to the critical value, critical impact parameter BC. So notice that here the photon sphere is the critical, acts as a critical boundary for photons which falls inside the horizon, and photons which escape to a faraway observer. However, in the observer sky, if we take a projection of the photon sphere, the dark disk will not be equal to the dark disk will not have radius 3m. Instead, it will have a radius larger than 3m. That is because bending of light. So here you can see that the photon sphere has a radius 3m, but in the observer sky, it will appear at some greater radius, because we have to take a tangent at the observer sky. So at the observer point, that's why it will hit some different radius. So it will be at BC. For Schwarzschild black hole, it is 3√3m. This is because of the bending of light. Therefore, in the observer sky, that is in the alpha beta plane, we will see a dark disk having radius 3√3m. So now how to find a shadow or boundary of the shadow? So for that, what we first do is we find out the effective potential. Then we find out the unstable unstable photon orbits and the corresponding critical impact parameters. We put all those we put the critical impact parameter in this expression and find out what will be the critical locus in the observer sky of those unstable circular orbits. And then we get the shadow boundary. So remember that for this spherical symmetry case, the radial equation is given by this f by g r dot square plus v effective b square v effective equal to 1. Therefore, in order to find out, so suppose we have given a space-time geometry and we have found out the effective potential. So then what we do is we found out the unstable circular orbits. For that, the unstable circular orbit conditions are r dot equal to 0, r double dot equal to 0, and r triple dot must be greater than 0, since we are concerned about the unstable circular orbits. Now, in terms of the effective potential, these conditions boils down to these conditions. Now, if we solve the first two equations for a given space-time geometry, then we get two equations for the spherical symmetric case. The first equation tells us the photon sphere equation. For example, for Schwarzschild case, if we solve this equation, then we'll get r equal to 3m. And the second equation tells us the boundary of the shadow. So in this case, if we find out the critical impact parameter and put it in this alpha, put that critical impact parameter xi eta in this equation and take alpha square plus beta square, then what we find that the boundary of the shadow is a circle having radius bc. Remember that bc is the critical impact parameter. For Schwarzschild black hole, if I solve these two equations, if I solve the first equation, I get the photon sphere are equal to 3m, rph equal to 3m, and if I put it in the second equation, we get the boundary of the shadow. So the shadow is a circular disk having radius 3√3m. So now we have seen that if we have a photon sphere, then the photon sphere captures photon having impact parameter get less than the critical value. For black hole, these photons which are captured by the photon sphere eventually get absorbed by the event horizon, and hence we have a shadow. Now the question arises, since a photon sphere captures photons, therefore can we have a compact object which have a photon sphere but not any event horizon? Can such object cast a black hole like shadow? To demonstrate this, let us consider a class of horizonless object. We take JMN, Joshi-Malafarina Narayan space-time, which describes a geometry around horizonless compact object formed from gravitational collapse. So this geometry have two classes. So here I am considering only the first class, that is the JMN1 space-time. This space-time is given by this. So this space-time doesn't have any horizon, and it contains a naked singularity at the origin, and is smoothly matched to a exterior Schwarzschild geometry at this geometry at some radius rb, where rb is given by this. And of course, rb should be greater than the event horizon of this Schwarzschild black hole. Now, this chemistry diagram, if we look, then for the black hole case, we have this, for this black hole case, we have this central singularity, which is denoted by the red dot, and the event horizon as well as photon sphere. But for naked singularity, we can have, since we don't have any event horizon, so we have a singularity here and here, and we may have a photon sphere or may not have any photon sphere. So this is denoted, so if we, for this JMN space-time, if we plot the effective potential, then what we see is, so this is for Schwarzschild black holes. So notice that we have a maximum of the effective potential at r equal to 3m, Then for Schwarzschild black hole, we have a photon sphere. But for Zeeman space-time, if this m0 parameter, if this m0 parameter have a value greater than 2/3, then the effective potential looks like this. Therefore, notice that in this case, we have a maximum of the effective potential, and hence we have a photon sphere. And this case is denoted by this schematic diagram. However, if the m0 parameter is less than 2/3, then the effective potential diverges at the singularity. And in that case, since the effective potential doesn't have any maxima, so we don't have any photon sphere. And this is denoted by this schematic diagram. Therefore, notice that for this case, since we have photon sphere, the photon sphere will capture some photon, and those captured photon will get absorbed by the central singularity. Hence, this case will cast shadow. However, in this case, we don't have shadow as the effective potential diverges at the singularity. Hence, photons with any impact parameter will get deflected by the infinite potential barrier sitting at the singularity. So to confirm this, we considered optically thin spherical accretion onto the Schwarzschild black hole as well as onto the JM non-naked singularity, and produced the intensity map of the system. So the accreting matter will, as the matter get accreted, it will get heated up and emit photons. Those photons will undergo gravitational lensing by the gravitational field of the central object, and some of the photons may get absorbed, and some photons escape to a faraway observer. We collect all those photons and then make the intensity map of the system. So in these plots, we have shown the shadow of the Schwarzschild black hole, as well as for naked singularity, which have a photon sphere, also in the naked singularity for the case which doesn't have any photon sphere. Notice that if the naked singularity have a photon sphere, then it casts a black hole-like shadow. In the case when the naked singularity doesn't have any photon sphere, since all the photons get deflected back by the infinite potential barrier sitting at the singularity, then we have we doesn't have any photon, we doesn't have any shadow. Instead, we have a full moon image, and the plots in the second row shows the corresponding intensity profile along the x-axis. We also took thin accretion disk in the equatorial plane, optically thick, geometrically thin accretion disk in the equatorial plane, and produced the images of the system. So this is for Schwarzschild black hole, and the rest are for JM non-naked singularity. So this is the case. This is for the case when we have a photon sphere. Note that this case perfectly mimic the Schwarzschild black hole case. Whereas the other cases, this and this other cases have the central, the images contain some central extra images at the center. So this case differ from the Schwarzschild case. So the key point that should be understood from this is if a naked singularity have a photon sphere, then it can cast a black hole-like image or shadow. So let us now see what the Event Horizon Telescope group has to say about our results. So they have written a series of papers on their finding on the observation of M87, and in 2 of the paper they have cited our results. In the 5th paper, they have completely ruled out the naked singularity, which doesn't have any photon sphere. So in that case, instead of a field disk, instead of a shadow, we have a field disk with no dark region. So there they are talking about the a naked singularity which doesn't have any photon sphere and cast full moon image. So here they have cited our paper. And in the first paper, they have admitted that compact object which doesn't have any horizon, such as a naked singularity, so here they have cited our paper, they can also cast a black hole-like image or shadow. Let us now understand how we can use. So till now I have focused on only non-rotating case, that is spherically symmetric case. Now we consider the spinning case or rotating case and see how we can constrain these alternatives using the M87 results. So for this, so as I have said, the by alternatives, I mean either compact object which doesn't have any event horizon, or black holes whose gravitational field deviate from that of the Kerr black hole. Means I'm considering non-Kerr black hole. So here I take one example from each category. The first example is a horizonless compact object, HCO, with the exterior geometry being given by the Kerr metric, and it has a surface at r equal to r naught outside the r plus, means outside the outer event horizon of Kerr black hole. So this is the space-time geometry of a Kerr black hole, and the horizons are obtained by setting this delta equal to 0. So if I solve this, then we'll get r plus minus equal to r plus minus equal to m plus minus root over m square minus a square. This r plus denotes the outer horizon of the Kerr black hole, and the r minus denotes the inner horizon of the Kerr black hole. So this is shown in this schematic diagram. So this central red dot represents the singularity. So although I have shown this by central dot, but actually for Kerr black hole, this singularity is a ring singularity, and this inner black region shows the inner horizon, and this outer black ring shows the outer horizon of the event horizon, outer horizon of the Kerr black hole, and this red deformed sphere shows the location of unstable photon orbits. Now, so in spherically symmetric case, for example, for the Schwarzschild case, we saw that since we had spherical symmetry, then all the unstable photon orbits, whether it be on the equatorial plane or in off equatorial plane, they had the same radius, and that is 3m. So if we add all those unstable circular orbits, then we had a sphere of radius 3m, which we call photon sphere. But in the axially symmetric or rotating case, the scenario is a bit different. The photon sphere doesn't have a constant radius. Instead, it will get deformed. That is because in the rotating case, the spin affects motion of photons. So suppose this is our space-time geometry, this is our object, and suppose this rotates this way. So in the gravitational field of this object, we may have photons which moves in the direction of the spin as well as in the opposite of the spin. So the photons which moves in the direction of the spins are known as prograde photons, and the photons which moves in a direction opposite to the spin are known as retrograde photons. So the spin axis will affect the motion of these photons, and correspondingly the unstable circular orbits, even in the equatorial plane, will not have a constant value. So for example, if we take the equatorial plane, then unstable circular orbit have some radius, and if we take some off equatorial plane, the unstable, since the motion of photon in this plane gets affected by the spin, so the unstable circular orbits have a different radius. So therefore now we don't have, the photon sphere is not a doesn't have any constant radius. Instead it gets deformed. So this is denoted by this red circle, red means you can say a deformed circle. So this is actually a deformed sphere. So since I'm showing in 2D, so its projection is a deformed circle. So and now this means the unstable circular orbit radius so now the unstable circular orbit doesn't have a constant radius, means it has some minimum value and some maximum value. So the minimum value will be here and the maximum value will be here. Okay. So now for the horizonless compact object, we can have three cases. So this is the horizonless compact object. See this denoted by this gray disk. So it have radius r0, which is greater than the outer horizon radius of the would-be curved black hole. So we don't have any horizon. So in the HCO case, we can have three cases. In the first case, the HCO may be completely hidden within all the unstable circular orbits, or it may a part of it may be outside the unstable circular orbits of the curved black hole or curved geometry, or it may means this object may be completely outside this outer surface may be completely outside all the unstable photon orbits. So depending on the situation, we'll have the shadow will be different. So that we'll see in a moment. So next class of space-time means alternative that we consider is the rotating version of the Simpson-Visser metric. So the Simpson-Visser metric is given by this space-time. So here this is a deformation from the Schwarzschild metric, the deformation parameter being R0. So in this metric, by introducing this deformation parameter R0, the central Schwarzschild singularity is removed by a minimal surface having radius R0. Now we use a Newman-Janis algorithm to construct a rotating version of the Simpson-Visser metric, which we call RSV. Excuse me. And the metric is given by this. So notice that the metric is similar to the curved black hole, except the delta tilde term denoted by this red color. So if we set R0 to 0, then we have delta tilde equal to 1, and we have the curved black hole, which have with horizons at R plus minus. Now notice that in this RSB metric also we have horizons at R plus minus. However, depending on the relative value between R0 and R plus, the outer horizon of the curved black hole, we have different cases. So these different cases is shown in this schematic diagram. So if the minimal surface radius, this R0, is less than the outer horizon of the would-be curved black hole, then we have a non-curved black hole. Non-curved because we have this deviation parameter delta tilde. So this is denoted by this case. So this is this black outer ring is the outer horizon of the curved black hole, and this gray disk shows the radius of the minimal surface. And if the minimal surface radius is less than the outer radius of the outer horizon, then we still have black hole. So this we will see that this case will perfectly mimic curved black hole. However, if the R0 is greater than the outer radius of this event horizon, radius of the outer event horizon, then we have these three cases. So in that case, the horizon of the would-be curved black hole become immaterial. So we have a wormhole with the minimal surface R0 being the wormhole throat. And here this red deformed circle denotes the deformed photon and location of unstable circular orbits. So here also, similar to the HCO case, we have three cases where the in the wormhole case, we have three cases where the wormhole throat may completely be hidden inside all the unstable circular orbits, or part of it may be outside some circular orbits, or it may be outside of all the circular orbits. So depending on the scenarios, we will have different cases, and we will see shortly that the expression for shadow radius in these different cases are different. It can be shown that the RSB metric, the rotating Simpson metric that we have constructed, falls into a special class of most popular non-curve metric proposed by Johansson. So this is well celebrated metric in the GR community. So people use this metric to test possible deviation from curved black hole. So this metric is given by these metric coefficients. And here this A1, A2, and this tilde A5, these are given by this expression. And now, if we set this deformation parameter, say alpha 2n to 0, alpha 1n to 0, alpha epsilon n to 0, then what we get is the curved black hole. The RSB metric that we have just considered, we have constructed using Newman-Janis algorithm, can be obtained as a special case of this Johansson metric if we set all the deformation parameter to 0 except alpha 5,2, where alpha 5,2 is given by this. Excuse me. So let us now see how we can construct the shadows of these alternatives. So the details can be found in this paper. So for the curved black hole, if I solve the second order, integrate the second order geodesic equations and obtain the first order geodesic equations, then I said that the effective potential appearing in the radial geodesic equation is very crucial to obtain the unstable circular orbits as well as the shadow. So therefore, that's why I have written only the radial geodesic equation, which is given by this. So now here, if I square it and add, then we can say that this capital R is means similar to the effective potential. Therefore, in this curved black hole case, if I want to obtain the unstable photon orbits, then we have to use then this equation in terms of capital R becomes this. Now, if I solve this first two equation, and then we obtain these two expression for the critical impact parameter. So remember that the unstable photon orbit radius RPH is not constant in this case. In the Schwarzschild case, spherical symmetric case, RPH was 3m, but as I explained, in the axially symmetric case, RPH will have different value in the different plane. So if we put this critical impact parameter into the expression for alpha beta, which relates the impact parameter to the point alpha beta in the observer sky, we get these two expressions. So if I put xi pH, eta pH in these two expressions and use RPH as a parameter by varying it from some RPH min to RPH max, then we'll get the critical locus of the unstable circular orbits in the observer sky, and hence we get the shadow boundary. So for curved black hole, the shadow looks like this. So this is the center of the in the observer sky, which is on which the coordinates is given by alpha and beta. So notice that so in the here the so this is the shadow boundary. Here the unstable circular orbits which have minimum radius corresponds to this point, and the unstable circular orbits which have maximum radius, which is denoted by RPH max, corresponds to this point. So this was for Kerr black holes. Let us now consider first type of alternative, so which is the horizonless compact object with the exterior Kerr geometry. So this I have explained already. So this is for Kerr black hole, and for, as I said, for the horizonless compact object, the radius is greater than the outer horizon of the Kerr black hole. So here the horizon becomes useless. So and here we can have three cases. So if this corresponds to RPH mean and this corresponds to RPH max. So if RPH are not the radius of the compact object is less than RPH mean, then the compact object is completely hidden inside the all the unstable circular orbits. Therefore, in this case, since the exterior geometry is given by the Kerr geometry, then the unstable circular orbit surrounding this object will be the same as that of the Kerr black hole. Therefore, this case will perfectly mimic Kerr black hole. However, if the radius of the object is less than between RPH mean to RPH max, then some part of the object will be outside of some of the unstable circular orbits. The unstable circular orbits which falls inside this object will now become immaterial. Therefore, this part of this unstable, this part of the shadow will be given by the unstable circular orbit of the exterior Kerr geometry, which is the Kerr black hole. And this part of the lost part, so this we call lost part. So since this falls inside the object, so and the inside we don't have any Kerr geometry, so this lost part will be given by the photons which have turning point at the surface of this object. And the turning point means we have r dot equal to 0, and r dot equal to 0 means we have capital R at the surface equal to 0, and this is given by this expression. Therefore, in this case, the shadow will be given by this part of the shadow. Sorry, let me erase it. So therefore, in this case, this part of the shadow will be given by those of the Kerr black hole, and this part of the shadow will be given by a turning point or by this equation. However, in this case, since all the unstable circular orbits of the Kerr black hole falls inside the object, so those orbits become irrelevant. So in this case, the shadow will be given by the shadow will be given by the turning point of photons, given by photons having turning point at the surface of the object, that is by this equation. Now for the RSB metric, if I solve the geodesic equation again, and then we have the radial equation is given by this. So note that we have this extra parameter. Rest is very similar, is the same as the Kerr black hole. So as I said, for the RSB metric, we have 4 cases. In the first case, if the R0, the minimal surface is within the outer event horizon of the Kerr black hole, then we have RSB black hole, which is a non-Kerr black hole. So in this case, since the exterior metric is given by the RSB metric and the radial part of the geodesic equation is given by this equation, then in this case, if I solve for the unstable photon orbit radius, that is for r dot equal to 0, r double dot 0, r triple dot greater than 0, then in terms of this effect, capital R, these are given by this. Notice that for this outer part, these unstable photon orbits are unaffected by this extra term. Therefore, these unstable, in this case, the unstable photon orbit, which is outside this object, will be the same as the Kerr black hole. Therefore, this case will perfectly mimic the Kerr black hole. In this case, we have in the when the R0 is outside this minimal surface, the radius of the minimal surface R0 is greater than the outer radius of the outer event horizon of Kerr black hole, then we have these 3 cases. So these 3 cases correspond to wormhole case. And if the surface has a radius less than this RPH mean, then what we see that the throat is completely hidden inside the all the unstable circular orbits. So in this case, the unstable circular orbits, and hence the shadow will be given by the same expression as those of the Kerr black hole. So this case will also perfectly mimic the Kerr black hole. In the third case, if the radius of the throat is between RPH mean and RPH max, so this is RPH mean, this is RPH max, then some unstable photon orbit become irrelevant as their radius become less than the throat radius, and throat radius is the minimum radius that we can access. So therefore, in this case, this outer part of the shadow will be given by those of the Kerr black hole, and the lost part, which corresponds to this part, will be given by the unstable circular orbits which are located at the wormhole throat. So we know that wormhole throat may also act as the location of unstable photon orbits. So therefore, this lost part will be given by the unstable photon orbit which are located at the throat, and therefore in this case, so that means for this unstable circular orbits which are located at throat, this term vanishes. So because at r equal to r naught, if we put r equal to r naught, where r naught is now the radius of the unstable photon orbit, so this term vanishes. That means r dot equal to 0 is satisfied automatically. Therefore, if we solve for the unstable photon orbits at the throat, then these conditions turns out to be this. Notice that this is bit different from the unstable circular orbit which lies outside the throat. So here we have r equal to 0, r prime equal to 0, r double prime greater than 0. But here we have r equal to 0, r prime greater than equal to 0. One less derivative, that is because we have this extra term, and because of this extra term we have additional 0 at the throat. So therefore the unstable circular orbits which lies at the throat will be the part of the shadow due to those unstable photon orbits will be given by this equation. In this case, since all the unstable circular orbit of the exterior geometry of the Kerr black hole lies inside the wormhole throat, so all the unstable circular orbits of the Kerr black hole become irrelevant. So in this case, the shadow will be given by the complete shadow will be given by unstable circular orbits which lies at the throat. That is, will be given by this equation. So this first, three plot shows the shadow. So now one thing we can notice that the expression for the shadows for this RSB metric as well as for this RSB metric as well as this horizonless compact object are the same, because this equation as well as the equation are the same. Therefore, from now onward, we will not refer to any. We will not separately referred to RSB metric or horizonless compact object. We'll combinedly call them alternatives. So this plot shows the shadow of the alternatives. Notice that when this R naught by R plus, so R plus is the radius of the outer horizon of the Kerr black hole. So it is. So I have said that when R is less than R plus, R naught is less than R plus. That is when R naught by R plus is less than 1. That case perfectly mimic Kerr black hole. So we are not considering that case. So if R naught by R plus is greater than 1, means if the wormhole throat or the surface of the compact object lies outside the event horizon of the outer event horizon of the Kerr black hole, then we may have some deviation in the shadow. So here we have shown for 3 R naught value. Then notice that for the first case, here the black curve shows the shadow of the Kerr black hole, and black plus blue dashed curve shows the shadow of the alternatives. Note that for smaller R by R naught values, the shadow doesn't, the shadow of the alternative is very similar to, is the same as the curved black hole. However, if we increase R naught, then we see that the shadow of the alternatives start deviating from that of the curved black hole. Therefore, R naught should have a critical value above which the shadow gets deviated from that of the curved black hole. So since shadow get deviated, then as a result, its angular, its radius as well as deformation from circularity will also get deviated, will also be different from curved black hole. Therefore, we use this average radius as well as deviation from circularity to as observed from M87 to constant these alternatives. So for that we first, so notice that this was the center in the observer sky. Now because of the spin, the black hole shadow or the shadow of the alternatives gets deformed, and also it gets shifted on the right side. So the spin is along this direction. Therefore, in order to find out the average radius, so this shadow have different radius, it doesn't have a constant radius. So what we do is we find average radius of this shadow. To do this, we have to first find out the geometric center of the shadow. Since we have if the geometric center is given by alpha c beta c, then the expression for this geometric center alpha c and beta c are given by this. So alpha is c equal to 1 by a into alpha dA, integration of our alpha dA, where alpha is any point, alpha beta is any point in this shadow, on this shadow curve, and beta c is 0 because we have symmetry around this reflection symmetry about this alpha axis. That's why beta, the center will lies on the alpha axis, that is beta, the beta coordinates of the geometric center will be 0, and the alpha coordinates is given by this expression. So for therefore, once we find out the alpha coordinates and the geometric center, then we find out the average radius of the shadow is using this expression. So let us now understand what is this expression. So from this geometric center, we define a radius L, phi, where phi is the angle between alpha axis and this line joining the geometric center and any point alpha beta on the shadow curve. And once we find out that L phi, we take another, say, small area element between phi and d phi. So this is d phi. Okay. So now if we find out the area of this triangle, the area will be half into L into L d phi, right? So this will be half L square d phi. And if we integrate this over the whole shadow curve, and then we get the total area of this object, total area of this under this curve. And if we equate that curve with if we replace that this shadow with a circular shadow with the equivalent radius of radius RAV, with the equivalent area with radius RAV, say, so this should be equal to pi R average square, pi R square. And from this we get the R average expression for the R average. So this is given by this. Also, so if we integrate this, then we will get the average radius. Also, we define the deviation from circularity as by this expression. So suppose, so let us understand this, how this works. So suppose we have defined this, so this is our geometric center. So suppose we have obtained, with respect to this center, we have obtained a equivalent, means we have obtained a black disk of radius RAV, which have a radius equivalent to this, means we have a area which have a area equal to this shadow, then that will look like, say, this. This is a, suppose this is a radius of R average. So for that, why we at a given phi, what we do is, so this was our L, okay, and this is our R, capital R. So we take deviation from this average radius. So this will be L minus capital R. Take square of this, and then integrate for all phi, and this is given by, so this is given by this equation. So this is basically the RMS distance of the L, RMS distance of L from this average radius R, and that will give us the deviation from circularity. If we have a circular shadow from the beginning, then L will be equal to R average, and then in that case we'll have delta C equal to 0, means there will be no deviation from the circularity. Now we calculate this average radius as well as deviation from circularity for different R0 and spin value, and this is shown in this plot. So this is not the average radius, but the average diameter. So d shadow is equal to 2R average. So here we have plotted average diameter of the, in the first plot we have plotted the average diameter of the shadow. In the second plot we have plotted the deviation from circularity as a function of this radius R0 and the spin value. Now for the M87 supermassive compact object M87, the parameters are given by this. The distance to the object is this 16.8 plus minus 0.8 megaparsec. So sorry, here it will be MPC, megaparsec, and the mass of the object is this. The inclination of the central object is 17 degree, and as reported by the EST collaboration, the shadow has an angular radius of 42 plus minus 3 microarc second, and the spin of the compact object lies in the range 0.5 to 0.94. Therefore, if we use these results, then we find that the dimensionless diameter of the shadow must be within 11.0 plus minus 1.5. That means it should have a range of from 9.5 to 12.5. Now, in the first plot, we have shown from the first plot, we have by this vertical dashed line, I have shown the spin range as reported by the EST collaboration. We note that within this spin range, the minimum shadow diameter is greater than 9.75. So we are safe. So this lower bound on this. So on this shadow diameter is satisfied in our case. However, in order that the shadow diameter should be below 12.5, so this 12.5 curve is given by this curve. For this spin range, then the R0 should have some maximum, should have some maximum value for a given spin. For this spin range, for example, for the spin 0.5, the R0 should have a maximum value of 2.54. And for the spin 0.94, R0 should have a maximum value of 3.51. And therefore, you notice that if the alternatives have a radius less than or in this region, then its shadow will be consistent with the observed shadow of M87. And for the deviation from the circularity, we see that for all spin for the spin range as reported by the M87, as well as for all R0 values, the deformation from circularity is less than say 0. So if this say this is 0.006. So if I multiply it by 100%, so it will be basically 0.6%. So according to EST, the deformation from the circularity should be less than 10%. So this is, so our result is within well below the 10%. So this is consistent with the M87 results. So we hope that an increase in precision in the EST data should improve the constraint that we have reported here. So this is the constraint. So the R naught have a maximum value, R0 max, and that maximum value should be between 2.54 to 3.54 for the spin range 0.5 to 0.94. So with this, I conclude and stop. Thank you. Hello.
So, Ravi,
Yes.
Okay.
Hello.
Yes. Yes.
Student, you have any questions?
So,
I have one question to Ravi.
Yes.
My question is: suppose you have a black hole, right?
Yes. Yes.
If you have a black hole, it is a three-dimensional picture, and when light comes from outside, and
Yes.
it may scatter or something do, and then you will get instead of getting a circular shadow, you are getting a deformed shadow, is not it?
Yeah. In case of rotating black hole.
In case of rotating black hole. Now, in the case of a wormhole, when you are considering a wormhole throat,
Yes.
so wormhole throat, in which direction you want to see? If you want to see it vertically, that means then it is like a point, right? It is like a point, and if you just cut it, it is like a spherical. It is like a circular. No, it is very difficult for me to understand the
No, so
wormhole.
no
You
for
explain?
no for wormhole is, so are you talking about the inclination angle?
At an angle.
Yeah. So as I said, the means for wormhole, if you have a circle, say spherical throat, okay,
Yes.
and if the unstable circular orbits in the exterior geometry, all those unstable circular orbits lies inside the throat, then we'll see only the throat. Okay, so in that case the shadow will be circular. But as I have mentioned, different cases, depending on the situation, the throat may some part of the throat may be outside the unstable circular orbits which lies outside the throat, or it may completely be hidden inside all the unstable circular orbits. So if the some part of the means if all the circular orbits lies inside the throat, inside the throat means it's the radius of all the unstable circular orbits will be less than the throat radius. So in that case, the outer light rings or photon unstable circular orbits become irrelevant. Then we'll see the throat only. So in that case, it will be circular.
Okay.
Also, it means not perfectly circular, because see when we see, so we have photons which move in a direction of the spin as well as in the opposite to the spin. So these two types of photons will undergo gravitational diffraction differently. So do you get it?
Yes, I understood.
Yeah,
There was a question when Farooq was giving lecture by Dipankar Pal, I think.
Okay.
He asked if you see a shadow, how can you identify that it is from a black hole or from a wormhole?
So
What thing you study?
so in today's talk I told that if the wormhole or this compact object have a radius less than certain maximum value, then it in that case its shadow perfectly means shadow means contour perfectly mimic that of the curved black hole. So in that case, in order to distinguish them, so from this only the shadow contour, you cannot distinguish between them. So in order to distinguish them, you have to then consider, say, uh, uh, accretion flow around these objects, because the exterior geometry will be very different. Then the quantitative differences, say the spectrum that the observer observed or received from the accretion flow, emission from this accretion flow will be different. From those spectrum, may possibly you can distinguish between the two.
Rajul, I,
Yes.
I just a query. So, is it possible to study any strange star or compact star for the shadow type study? Is it possible?
Now here I have taken, so in the first class I have taken a horizonless compact object. So in that case the radius is R naught, and inside whether it's a strange star or thin cell wormhole or a grava star, that I didn't mention. So I have considered a complete general class, and I am not bothered about the space-time geometry inside that object, because here I have considered that that surface is completely absorbed. So once all the photons which hit that surface get absorbed by this case. So
Oh,
Okay.
yeah.
good, good. So very
Okay.
fine lecture. Huh? Okay. Tell.
So once again, I would like to thank distinguished speaker for their valuable time to attend to participate the webinar, and I would like to also thanks Professor Vikas Chandra Pal to organize such a beautiful program and organizer, and thank you all. And now I hand it over to Professor Vikas Chandra Pal for the next session.
Thank you, Professor Praveen Kumar Haldar, for your nice involvement in the program and giving us your valuable time with us. And I hope that everybody enjoyed the first two talks. You are invited, all of you are invited for the second contributory talk starting from 2:30. And I also request everybody to be present around 5 p.m. because we have a we have a valedictory session with a photograph. Right, photograph like yesterday's in the screen. So I request everybody please come at 5.
Thank you.
But gather at 2:30 only for the chairman and others. They can come at 5, but others please come at 2:30. Thank you.
Thank you.
Thank you. Thank you.
No lunch break.
Thank you.
হ্যালো। এই তো এই তো চলছে। তোমার কাজকর্ম কেমন চলছে? হ্যাঁ, বাকিরা কোথায়? অনির্বাণ, বিনয়? অনির্বাণ, বিনয় কই? ও, ভালো ভালো, বেশ ভালো, দারুণ। এই সেশনটা আরো ভালো লাগতো, অনেকেই আছে। ফার্স্টে তো পিয়ালি ভার নাকি? পিকেসি স্যার, পিকেসি স্যার মনে হয় ক্লাস নিচ্ছে নাকি? মনে হয় ক্লাস নিচ্ছে। হ্যাঁ, এলাকায় তো।
হ্যাঁ ভালো। তুমি কেমন আছো? ল্যাবে যাবো। তোমার তো ক্লাস তো এখনো কিছু নোটিশ দিচ্ছে না, ক্লাসের কি হবে না হবে। আর এমনি ভেরিফিকেশনের কোনো নোটিশ এখনো কোনো ফার্দার কোনো কিছু দেয়নি আর।